For this video, we will be discussing the use of subelements and layers. These features are useful for constructing a model that is simple and organized. A model is always composed of one or more elements. These are the basic building blocks that we use to create shafts, casings, and other structures. Sometimes it can be useful to break an element up into subelements. For example, when you are modeling a complicated geometry with small features. Subelements can be a good way to get overall mass distributions right without using an enormous amount of elements. Subelements mainly function as a way to condense a complicated set of elements into a single entity. This is similar to finding the equivalent stiffness for two springs. When you use subelements, you're always taking an element and chopping it up into smaller segments. It can be helpful to think of the element naming convention in terms of groups. For example, the first row in the table is element 1, subelement 1. For the second row, it is still element group 1, but subelement 2. If you look at element 2, you can see that it doesn't contain any subelements. However, the table shows element 2, subelement 1. This is because the table always lists the first part of an element as subelement 1. Even if that element is not split into subelements. Stations define the beginning and end of an element. Substations are used to chop an element up into its subelements. Two methods are shown on the screen for modeling the same piece of a shaft. The method on the left does not use any subelements, and the method on the right does. For each model, the shaft element sheet is shown below. The two cases produce identical results when an analysis is run, but the case on the right is solving a more condensed set of equations. In the first case, element 1 goes from station 1.1 to station 2.1. Another way of saying this would be that it goes from substation 1 of element 1 to substation 1 of element 2. In the example on the right, element 1 is split up into two subelements. The first subelement goes from substation 1 of element 1 to substation 2 of element 1. The second subelement goes from substation 2 of element 1 to substation 1 of element 2. Two things to note about subelements. Be cautious with big changes in stiffness diameters between subelements within a single master element. Also, some of the functionality of elements are not available for subelements. For example, you cannot connect lump masses or bearings to subelements. Another important concept in Dyrobes is the idea of layers. The terms levels and layers get used interchangeably. Basically, what happens when multiple layers are used is the stiffnesses and masses are added together to produce overall element stiffness and mass. You can have multiple layers in a model. All of the layers of a shaft will bend together. If you want to model something that behaves like it is bonded to the shaft, then layers may be a good approach. Layers are not appropriate for things that will move relative to each other. Two layers can have completely different material properties and can also have different mass and stiffness diameters. For example, a coupling hub that is fit onto a shaft can often be modeled as a separate layer. Layers are zero-based. The first layer of an element will always be layer 0. Layers are assigned to individual elements and subelements, so it is possible to have elements next to each other that do not have the same number of layers. Here, you can see a case where layer 1 is removed from element 2 but kept for elements 3 and 4. Here's an example of how multiple layers can be used to model an assembly. There is a bolt holding an impeller hub to the end of a shaft. For this composite model, we have different materials for each level. At subelement 2 of element 5, we are only using two levels, one for the bolt and one for the impeller. And here on subelement 2 of element 6, we only need to use level 0 to model the end of the impeller. So in this model, part of the impeller was defined on level 1, and part of it was defined on level 0. So to summarize the numbering system for subelements and layers, subelements must be consecutive and start with 1. Layers must be consecutive and start with 0. For example, layer 1 cannot appear in the shaft elements table before layer 0 has appeared in the table. And also, the subelements don't all need to have the same number of layers. Another interesting thing about Dyrobes is that conical elements can be used. To do this, you need to put a negative sign in front of the subelement number to flag that it is a conical element. Once a row has been flagged as being a conical element, the mass and stiffness diameter columns are treated as left and right diameter columns. Because the mass and stiffness diameter input fields are used to define the left and right diameters, a conical element will always have equal mass and stiffness profiles. If you need to reduce the stiffness of a conical element without adjusting its mass, this can be done by adjusting the material properties for that element. Be careful not to create triangular elements. Dyrobes cannot handle elements where the ID and OD are the exact same. To summarize what we've talked about, subelements can be used to simplify a model and reduce unnecessary degrees of freedom. Layers or levels can be used to create more complex structures, and conical elements are easily defined within the shaft elements page once you know how to specify them.